Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. This is Module 5, Lesson 1, the concept of a function. Okay, classwork, example 1. Suppose a moving object travels 256 feet in 4 seconds. Assume that the object travels at a constant speed. That is, the motion of the object can be described by a linear equation. Write a linear equation in two variables to represent the situation and use the equation to predict how far the object has moved at the 4 times shown. Well, they gave us it's moving 256 feet in 4 seconds. So, number of seconds, motion 4, distance traveled 256. That was given. Okay, we're also told that it is a constant speed, and remember that constant speed c equals y divided by x. So if we have a y, we divide it by x, we find a constant. So if I don't know my constant, but I do know a y, and I do know a 4, then my constant is 256 divided by 4. I can also represent this as a linear equation in terms of y and x, and I think it did say that, write a linear equation in two variables. So I don't want to just find out what c is right away, but I can, and if I continue this way, 6 times 4 is 24, the remainder 1, 4. So my c is 64. We can also remember that this is y over x, and we have 256. It doesn't look like 256 to me. That's pretty messy. Let me rewrite that. 256 divided by 4. These are our two values that are equal to c. So if they're equal to c, they're equal to each other. So I will do this over here. Y over x equals 256 over 4. Cross multiply, and I'm going to get 4 times y, which is 4y, and 256 times x is 256x. And if I divide both sides by 4, the 4's cancel, and I get y equals 64x. So it's just this number here in front of the x. So there's my linear equation in two terms, y and x. Okay, so now I need to finish this table. So now I can just substitute values in. Y equals 64 times 3 would be for 3. When x is 3, what is y? Y equals 4 times 3 is 12, carry the 1. 6 times 3 is 18, plus 1 is 19, so that is 192. Then I do y equals 64 times 2, so y equals 2 times 4 is 8, 2 times 6 is 12, and that's 128. And then 64 times 1 is obviously 64, so I'm not even going to write that. So there is the table, knowing that we had a constant speed. Okay, example 2 says, the object, a stone, is dropped from a height of 256 feet. Okay, so we're dropping a stone from a height of 256. It takes exactly 4 seconds for the stone to hit the ground. So right there, after 4 seconds, how far did it go? Well, if it hit the ground after 4 seconds, then it went 256 feet. It takes exactly 4 seconds for the stone to hit the ground. How far does the stone drop in the first 3 seconds? So we want to figure this out here. What about the last 3 seconds? Can we assume a constant speed in this situation? That is, can the situation be expressed using a linear expression? So if you let go of a stone, so picture yourself standing at the top of a building, holding a stone over the edge, and you let go. As soon as it leaves your hands, does it go the same speed the whole time it falls from the top of the building down to the bottom? Think about that and try to answer this question. Okay, so in order for us to determine this, let's take a look at a video that was offered in the teacher edition. So I looked at it. It's actually a physics class from some school, and they dropped a ball from the roof of their school and they timed it. So we're going to watch this video, and I'm going to pause it and so forth. So here we go. So it's a video within a video. I've never done this before. So here's the video, And we have the students up here on the roof, and I'm going to pause the video right when he's ready to drop the ball, and I'm going to explain what we're going to do next. Okay, so right there you can see his hand just moved. So we're at a 6-second mark. Unfortunately, it's almost 7. 8 is all the way here, so I will stop the video. So I'm just trying to get an approximation of what 1 second is. So from here to here is where it changed to 7 seconds, right there. So I'm only that little distance beyond 7. So if I go only that distance beyond 8, that would be right about here. So there would be 1 second from when the ball drops, just beyond 7 to just beyond 8. Okay, so actually no, it's not beyond 7, it's just before 7, this far. So if I find 8, 8 is right here, I want to go back about this far. So there would be the 1 second mark. So when I hit enter, it's going to drop, and then I will pause the video again when it gets to that where the finger is pointing on the timer. So if I hit enter and hit enter again, there's 1 second. Okay, so if we were able to measure the distance from here to here, that's 1 second. And then if we measure it to the next second, the ball's almost hitting the ground. This is really difficult to measure because of the timing. So let's just do it again. And so I can't see if you can tell, but it looks like the ball is dropping. It speeds up. Okay, let's just say that. So it gains momentum as you go. Okay, so anyhow, there's that video. So it's gaining momentum as we go. So I can't assume a constant speed, because if we do assume a constant speed, then we're going to take that 256 is going to be c equals y over x, or 256 over 4. And 4 goes into 250, 4 goes into 25 6 times, and 4 goes into 16 4. So that's a constant of 64 feet. 64 feet the first second, and 64 feet the second would be 128, plus another 64 would be, is that right, 202? 64 times 3, 4 times 3 is 12, 6 times 3 is 8, 19, 192. 192. And is that what we had up here? Yes, it is. 64, 128, 192, 256. That would be assuming that it's linear. But if a ball is gaining speed, it does not have a constant rate, so we can't do that. So what are we going to do in this problem? Okay, so now I've brought some data in, and someone has done this actual activity, and they recorded dropping a ball 256 feet. And at t equals 0, we're up here. After 1 second, it traveled 16 feet. After 2 seconds, it went from 16 to 64, so it traveled a total of 64 feet after 2 seconds. And after 3 seconds, it traveled a distance of 144 feet. So if I take y over x, if my constant equals y over x, and I look at my first term, I get 16 over 1, which equals a constant rate of 16 feet per second. If I do that with the next one, I get 64 over 2, which equals half of 64 is 32. So it doubled in speed the second. And then if I do that again, 144 divided by 3, 4 times 3 is 12, remainder 2. 8 times 3 is 24, so then 16 plus 16 is 32, plus another 16 is 48, and then finally c equals 256 divided by 4, and that gives me my 6 times 4 is 64. So as you can see, the distance is changing every time, so it is not a constant rate of change. I can't call it c. So we cannot assume a constant speed in this situation. It was going 16 feet per second the first second, 32 feet per second for these two, and then 48 feet per second after 3, and 64 feet per second after 4. Okay, So what we'd have to do is we'd have to actually subtract the distance here and see how far it went each second. So 256 minus 144 is 112 feet per second after that last second. These are totals. Okay, so we cannot assume a constant speed in this situation, and this situation cannot be expressed linearly. Okay, so here's exercises 1 through 6. Use the table to answer the exercises 1 through 5. Exercise 1 through 6, 1 through 5. Okay, number of seconds, x. Distance traveled in feet, y. So we have already calculated this value, 116, 264, 3 144, 2 156. And those are right here, 16, 64, 144, 256. So all they've done here is put in half-second intervals. So we're narrowing it down more. So now it's every half second. So you see that in the first half second it went 4 feet, but then it went 16 in the first second. So the second half it went 12 feet. It tripled its distance. So name the 2 predictions you can make from this table. Well, one prediction is after 1 second, okay, it traveled 16 feet. That's one prediction. So all they're saying is make a prediction from this table. Just pick a value out of the table and how far did it go. After 2 1/2 seconds, it traveled how far? 2 1/2 seconds, 100 feet. There's 2 predictions we can make from the table. Name a prediction that would require more information. Well, what if we predicted something that's not in the table, in between somewhere? So how about name a prediction that would require more information. How far the ball fell after, how about 1.25 seconds? That would require more calculations. Okay, so that's what they're saying. We can predict values from our table, but anything in between would have to require more work required. We need more information to find that in those. Okay, so now they're coming up with this average speed thing. What is the average speed of the object between 0 and 3 seconds? And how does it compare to the average speed calculated over the same interval in example 1? Okay. So what they're asking us to do is to take the total distance, the average distance traveled over a given time interval divided by that time interval, and they want to know what the average speed is between 0 and 3 seconds. So average speed would equal time interval 0 to 3, that's 3 seconds. How far did it travel in 3 seconds? So I go up and look in my table, and 3 seconds it was 144 feet. So the average speed is 144 divided by 3. 3 goes into 14 4 times, 12, and remainder 2. 3 goes into 24 8 times. So it traveled 8 feet, or 48 feet is the average speed per second. We now need to compare it to example 1, so I'll go back. Example 1, after 3 seconds, it went 192 feet. So I'm going to do the same calculation. So from example 1, it went 192 feet in 3 seconds. So that equals 3 goes into 19. 6 times 3 is 18, with the remainder 1 and 4. So 64 feet per second is the average speed from the original one. And this one was 48 feet per second. Okay, so that is the difference. Number 4, take a closer look at the data for the falling stone by answering the questions below. How many feet did the stone drop between 0 and 1? So I go back to the table. Between 0 and 1, it dropped 16 feet. Okay, so I will just put 16 feet here. You should say the stone dropped 16 feet between 0 and 1. How many feet did the stone drop between 1 and 2 seconds? Okay, again, I'm going to go back. And between 1 and 2 seconds is from 16 to 64. So I would say 64 minus 16 is going to be 48. So it dropped 48 feet between 1 and 2 seconds. Now between 2 and 3, so I go back, so it's 64 to 144. So I say 144 minus 64, and that's 0, and that's 8. So it's 80 feet. And between 3 and 4 seconds, 3 was 144, 4 was 256, so 256 minus 144, 112 feet. I forgot my 0 here, it's 80. So 16 feet, then 48 feet, then 80 feet, then 112 feet. So these are all 1 second intervals. So we see the thing is going in a faster rate because it's falling farther in the same 1 second intervals. E says to compare the distances the stone dropped from one time interval to the next. And what do you notice? Okay, so now it's not adding the same amount each time. So what else can we do repeatedly? That's the next thing we need to check. Okay, so now if I'm going to take these values and see what the difference, how much did it change from 16 to 48? If I take 48 and subtract 16, and that's calculating what the difference in feet is. 8 minus 6 is 2, 4 minus 1 is 3. So it went 32 feet further in second 1 to 2 than it did 0 to 1. And then if I do the same thing here, and if I take 80 and subtract the last second's distance of 48, then I get 10 minus 8 is 2, 7 minus 4 is 3. So it added another 32 feet to the distance. And then if I take the 112 and subtract 80, again, we're going to get 32 feet. So it is increasing a distance of 32 feet every second. That's how much faster it keeps going. Okay, and so it says compare the distances. What do you notice? 32 feet was added to each distance every second. Okay, number 5. What is the average speed of the stone in each interval? 0.5 seconds. For example, the average speed over the interval from 3.5 seconds to 4 seconds is distance traveled over a given time interval, 256 minus 196 over 4 minus 3.5. So what they're doing is they're just looking at these values, and they're saying 256 minus 196 divided by 4 minus 3.5. So the difference in your y's divided by your difference in your x's. Sound familiar? Okay, hopefully. It's slope or rate of change. Okay, so when they did that, they got 256 minus 196 is 60. 4 minus 3.5 is 0.5, which equals 120 feet per second. Repeat this process for every half-second interval, then answer the questions that follow. Interval between 0 and 5. So here we go. Unfortunately, we have to keep going back and forth, but let me clear this. And actually, here's what I will do. I will copy this and bring it to the next page. One moment. Okay, so here's that table, so I don't have to keep going back and forth and back and forth. So here we go. So interval between 0 and a half. So that would be, we're taking distance traveled, 4 minus 0, the beginning, divided by time, 0.5 minus 0. Okay, because what we're doing is distance traveled over a given interval. So it's the distance, 4, and when we don't start, we're at 0. So when I get that, I get 4 minus 0 over 0.5, which equals 8 feet per second. Now if I do it between 0.5 and 1, now it's these. Okay, so it's going to be y16 minus y2. y2 minus y1 over x2 minus x1. 1 minus 0.5. So that's going to be 16 minus 4 is 12 over 1 minus 0.5 or 0.5. And 12 divided by a half is 24 feet per second. Okay. Now I'm going to do 1 and 1.5 seconds. So we're doing this now. 1 to 1.5 is right here. So it's 36 minus 16 divided by 1.5 minus 1. 36 minus 16 is 20. 1.5 minus 1 is 0.5. And that's going to give me 40 feet per second. Okay, and we're going to keep doing this. Interval 1.5 and 2 seconds. So now we're doing this interval here. So it is y2, 64, minus y1, 36, divided by x2, which is 2, minus x1, which is 1.5. 64 minus 36 is 28, divided by 0.5. 28 divided by a half, or times 2, is 56 feet per second. Okay. E. Okay, we're still doing this. Okay, so I see a pattern already when we did these. So if you look at these, 8, to get from 8 to 24, I had to add 16. 24 plus 16 is 40. 40 plus 16 is 56. Okay, I'm going to keep going, but I do see the pattern here. So let me copy this over, go to the next page, paste it in, and keep going, just so we have our data. Actually, I'm going to put it above this time, so I can move up far enough because we're now between 2. Enough is showing. Okay, so now we're going to do interval 2 to 2.5, which is here. And that is going to be y2, 100, minus y1, 64, divided by 2.5 minus 2, which is 36, divided by 0.5, which is 72 feet per second. Okay. Next one. 2.5 to 3 is right here. y2, 144, minus y1, 100, divided by x2, which is 3, minus x1, which is 2.5. So as you notice, we're getting 0.5 every time in the denominator because we're doing the same interval each time. But the distance is changing. 144 minus 100 is 44. And 44 divided by half is the same as 44 times 2, which is 88 feet per second. And as you can see, 72 plus 16 is 88. So it's that same, yeah, 16. So it's the same amount each time. And now we're going to do interval from 3 to 3.5 in blue, which is here. And it's 196 minus 144 divided by 3.5 minus 3. So that is going to be 6 minus 4 is 2, 9 minus 4 is 5, divided by 0.5, which is 52 times 2, or 104 feet per second. So it went from 88 to 104. Compare the average speed between each time interval. What do you notice? Okay, the average speed between each time interval is increasing. It is, meaning the average speed is increasing by, can't write, by 16 feet per second. Okay, number 6 says, is there any pattern to the data of the falling stone? Record your thoughts below. Okay, so if we are multiplying, so here is time interval 1, it went 16, 2, 64, 3, 144, 4, 256. 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. 2, 56. Is there any pattern? So I'm going to pause this, see if you can find any pattern, see what you come up with, and then I'll come back and we'll talk about it. Okay, so one thing I noticed is 16. 16 is 16 times 1. And 64 is 16 times 2 is 32 times 2 is 64. So 16 times 4 is 64. And 16 times, let's see, 16 goes into 144. Let's see, 4 times, 9 times. 10 is 160, minus 16 is 144, so it's 9. 16 times 9 is 144. And 16 will go into 25 once, with a remainder of 9, 96. 16 goes into 96 6 times. So it's 16 times 16. So this is 16 times 1, 16 times 2, 16 times 3, 16 times 4. But it's not. It's 3. What do you do to 3 to get 9? What do you do to 4 to get 2 to get 4? And what do you have to do to 4 to get 16? Well, it's 2 squared, 3 squared, 4 squared. All right, so we're squaring the time interval and multiplying that square by our distance. That's all I'm going to say about this at this moment. We're leading up to something. That is the end of lesson 1. Review this summary and go do your problems.